Alrighty, welcome back to 105. So today, this lecture is fun because it's more sorting and it's nothing that you'll be tested on. So we get to have fun today. So we will touch on one more sorting algorithm. The other sections are behind us. So I will teach you something useful. So don't have to take notes if you don't want. We can just sit back and enjoy. So I put in yellow. Anything in this lecture is not testable, so we're going to go over 3 sorting algorithms, 1 really good one, and 2 unbelievably stupid ones. So first one, we will do a good one. So quicksort, all the sorting algorithms we saw before were like n squared, so they were really, really slow if you remember that graph. Quicksort is a sorting algorithm that is n log n. And how it works is we select an element as a pivot. So we just select one element. So in the case they're numbers, we just select one number. And our goal is we want to place everything less than the number to the left of that number and everything greater than that number to the right of the number. And this is called partitioning. And then after this, we can use our knowledge of recursion. And now we kind of separated the problem into 2 smaller subproblems. So we can now sort the left side of the pivot because they're all less than that number, and also sort the right side of the pivot because they're all greater than that number. So they are kind of already sorted, and that is how the algorithm works. So the main part of this is called partitioning, and we can walk through it really quick. So here is our array we would like to sort. It is 8 numbers, so the indices are 0 all the way up to 7. And those are all the values, so 10, 14, 8, 13, 20, 3, 6, and 9. So it is definitely not sorted. So how this algorithm works is it chooses a pivot. So you can choose it as the first element, the last element, the initial pivot as the middle element. Doesn't matter. In terms of making the programming task a little simpler, we will choose the last element as the pivot. So our goal here is we're choosing 9 as a pivot. So we want to move it somewhere in this array and swap any values we need to, such that everything to the left of 9 is less than 9, and everything greater than 9 is to the right of 9. So we want to get all the numbers smaller than 9 somewhere to the left, all of the numbers larger than 9 to the right, and then we want to place 9 wherever it goes. So how the algorithm will work is I will use a green arrow that will just signify where we want to place 9. So initially, we would place 9 at the beginning. If we just go ahead and swap 9 at the beginning, that should mean that, well, there is nothing less than 9, and everything else should be greater than 9. So clearly won't be the case here, but that is our initial starting. We're going to use this green arrow to represent where the pivot should go. So how this will work is we will iterate over every single element not including the pivot, and if the value is less than the pivot, we're going to swap it to wherever the green arrow is pointing, and then move the green arrow 1 over to the right. And then the idea is once we're done, well, the green arrow points to where the pivot is, so we will just go ahead and swap 9, like the last element, wherever the green arrow is, and then suddenly that will be our partition. Everything to the left will be less than, everything to the right will be greater than. So everything will be comparing relative to the pivot. So first, we would compare element 0 to the pivot. So 10 is greater than 9, so we don't swap anything. We don't adjust the green arrow. We just leave it as is. And then check the next element, 14, also greater than the pivot, so we leave it alone. Next thing we compare it to index 2. The element there is 8, which is less than the pivot, so we want to make sure that once we are done, that 8 is to the right, or sorry, 8 is to the left of 9. So what we're going to do is we are going to swap 8, so we're currently comparing to index 2. So we're going to swap index 2 with whatever the green arrow is pointing to, index 0. So after we swap, it will look like this, and we update the green arrow. So we swapped index 2, index 2 and index 0, and then updated the green arrow. So this means if we stopped right now, we would go ahead and swap in 9 with whatever the green arrow is pointing to, and then, well, 8 is to the left of the pivot because it's a smaller number. All right, on the same page with this, we're all good? Okay, so that was us looking at element 2. Next time, we're going to look at element 3. 13, greater than the pivot, not going to do anything. 20, greater than the pivot, not going to do anything. 5, less than the pivot, so we're going to do the exact same thing. So we're going to swap the index 5 with now whatever the green arrow is pointing to, index 1, and then update the green arrow to go forward 1, because we want to move, that's where we would want to put the pivot. So we swap 3 in, swap 3 and 14, and then update the green line. So now if we stop now, we would place 9 here, and then everything to the left is less than 9. All right, last element we have to look at is 6, at index 6, funnily enough, and then it is less than the pivot. So same thing, we would swap that and 10, and then increment the green arrow, and then it looks like this. And then now we're pretty much done. All we have to do is swap the last element with where it should go. So 9 should go where the green arrow is, so I swapped 9 and 13. So now it looks like this. And now it is successfully partitioned. So 9 is placed at index 3, and then everything to the left of 9 is less than or equal to it, and then everything to the right is greater than or equal to it, right? It's all greater than. So then after this, we can, if we define the problem right, well, we can recursively sort this side. So this would probably pick the pivot as 6, and then you go ahead and rearrange it such that we got 6, 3, and 8, which would then be in order, and then we could go ahead, have our recursive base case that, like, if we're sorting a single element or nothing, then we can just exit, and then it would be sorted. So this is quicksort. So quicksort, we could just define it using, an array and array length, but we're going to have a helper because our quicksort is going to take the index to start at and then the index to end at, because we're going to try and sort smaller arrays. So our base case is if low is less than or equal to high, because low should always be less than high. And then we write partition. So initially we partition the whole thing. And what the partition does is it does that algorithm and then returns the index where the pivot is. So in this case, it would return the pivot as being at index 3. So in this case, it would return the index as 3, and then we run quicksort on everything from 0 to, well, 3's in the right place. So index 3 is at the right place. So we can sort elements 0 all the way to 2. And then we can also sort the elements 4 all the way up to whatever we had, 7. So then this would just run recursively over and over again, and we have lots of fun. So any questions about that? We don't really have to understand this if we don't want. You will thank me for this, introducing you to this later, because this will come up again in an algorithms course next year probably, where you actually do have to understand this. So you may or may not thank me for actually introducing it to you now. So other things, the partition code, I mean, if you did what I did in undergrad and search Google, You would probably come up with code like this, and this is fairly ugly. It kind of gets the idea. So it saves the value of the partition. So in that case, our case, it was 9. It does some weird stuff, like it sets I, which is supposed to keep track of like where the pivot goes to, starts it off at low -1, which if we're starting it off with the whole array, would start off at 0 -1, which is -1, which is kind of weird. And then they iterate over every single element, including the pivot, because it's at high, which is weird to me. And then this is the code where it's, oh, if the element I'm currently looking at is less than the pivot, then I'm going to have to swap it in and update I. So I need to move where my pivot needs to go. And then after this whole for loop runs, which is what we did in the example, then it increments I and then swaps I and high, which is where the pivot is. So yeah, I don't like this code for several reasons. One, checking the pivot and then starting off at low -1 and then just remembering this increment after, kind of weird. So I would probably rewrite it like this. So start I equal to low, which is kind of what we did in that example when we went through it by hand. And then in the loop, I'd have j less than high, not equal to, because, well, I don't need to check the pivot because I'm storing the value in the pivot variable. And then I could just check that, have a little optimization here that if the number is already the smallest number, I don't try and like swap it with itself. That would be weird, so I just checked if I does not equal j, then swap, and then just like I wrote on the board, I increment after I swap things, and that saves me having to increment it after the loop. So after the loop just swaps the pivot to wherever it needs to go. So questions about that? So it actually works. So let's go ahead. If we go ahead and run this, boom, build quicksort. Hey, it actually sorts the array. Cool, recursion. So there are other recursive sorting algorithms if you really want to. If you want to Google search, there's one called merge sort. That's probably the next easiest one if you're interested in this. But quicksort is typically the one that's actually used when you're sorting numbers and sorting strings and anything like that. So quicksort is probably the first sorting algorithm you'll see that is actually in use. So sometimes people will use insertion sort for not that many elements, but for anything large, it will probably use something like quicksort. All right, now onto the fun joke sorting algorithms. All right, so I put in red to never use these, but there's an algorithm called bogosort, and everyone loves bogosort because with the real life analogy, how bogosort works is if I just, you told me to sort a deck of cards. If I went, oh, okay, I know how to do this. I took the deck of cards, I threw it in the air, I picked up the cards randomly, and then I checked whether or not they were sorted. And if they weren't sorted, I just repeated it. So they aren't sorted, I throw them up in the air again, pick them up randomly, check if they're sorted. If they're not, I throw them up in the air again. Yeah?
What's the big O for that?
Big O for that is n factorial, average case. So n factorial, not good. So if you think of like how factorials grow, yeah, it gets really bad really, really, really quickly. So what? Like 100 factorial is, well, 10 squared is 100. 10 factorial is what, some like 3 million, something like that. So it gets pretty bad. Yeah?
Is there a chance that given the same array, it would be faster than like quicksort if it just happens?
Yeah, so the question is there a chance that it is faster than quicksort? And the answer to that is yes. If the array is already sorted, you would check, is it sorted? Yes, it is. I'm done. And to check if the array is sorted, I just have to, that's like ON, right? I just have to check every pair of elements. I just have to make like n-1 comparisons to check if it's sorted. So in that case, it is faster. But how likely, but if your sorting algorithm only works fast if the array is already sorted, it's a pretty crappy sorting algorithm. All right, so bogosort sounds pretty stupid, right? Anyone think of anything stupider than that? Okay, there's one really stupid one called miracle sort. And what miracle sort does is just check if it's sorted, and then if it's not, it doesn't do anything, it just checks it again. So it hopes that a miracle happens, which the running time of that is probably infinite if it's not already sorted. If it is sorted, well, then it's the fastest thing on the planet. So we're all good. All right, slightly dumber than bogosort, and do not use these on an exam. This is like the one thing where like efficiency is questionable here, but even worse, there's something called bozosort, and that just randomly switches two cards and then checks if it's sorted. If not, repeat. So bogosort, you at least throw every card up in the air. For bozosort, you just make one swap, and that's it. So that seems fun, so let's implement it. So here's bozosort. I just wrote a function called inOrder that returns a Boolean whether or not the array is sorted. So to check that, that's pretty easy, right? I could start it at whatever I want. I decide to start it at 1 and then go to the array length because we have to check every single pair. So if the array at slot, I minus 1 is greater than I, that means, well, it's not sorted. So I can return immediately false. And then otherwise, if I check every single thing and all the elements are greater than or equal to, then I could return true that is actually sorted. So we can get some practice with our randomize. So how would I implement bozosort? So I'll start it off. So I need an index that's actually valid in that array because I want to just swap two random elements, right? So I could do something like this. So if I do ran and then mod array length, well, that will give me a number back between 0 and array length minus 1, which is a valid index, right? So that would be one index. I could write it like this, so just give me another number, and then I will just go ahead and swap them. So array I, array j. All right, that look good? Yeah, I could have an optimization, so here I can be equal to j, so maybe I don't want them to be the same thing because this is stupid, but that might be more than more stupidness than we would like to accept. So we could make this a little smarter. So what we could do is for j, it's like, well, if you think about it, the first number we can pick like array length things. For the second number, if we don't want to repeat, we should pick up to array length minus 1. And if I leave it as is right now, well, I could actually pick the same number. It could both be 0. So I probably want to add a check here. So one check I could have is if j is greater than or equal to I, then I want to increment j. And that will make sure, so for most of this, you kind of want to consider like the starting worst case, and then the middle case, and then the best case. So if rand mod this gave us 0, and then we got 0 back from j, well, we don't want them both to be 0. We would want at least the j to be equal to 1. So this is now where we check. So if they're equal, then we would increment j. So we would do swap index 0 and 1, which makes sense. And then if, I don't know, I was 0 and j was, I don't know, 3 or 3, then, well, incrementing j to be 4, probably not that big of a deal. But if we got the absolute last thing here, so say our array length was, I don't know, if our array length was 8, then what we might get for j is, if we do array length -1, that would be mod 7. So the biggest number we could get is 6. So if we got 6 back, well, that should actually represent the last index, which should be 7, because our array length is 8. So if we get 6, yeah, we should probably just increment j so we can make sure that we actually get the last element. So this bozosort, will it work? So here's my big array. I print the array, I bozosort it, and I print it. So will it work? Well, let's see. But like as written, is there any reason why it wouldn't work? It's just one of those things, right? That's just so stupid, there's no way it fails. So yeah, warning non-void. Bozosort. Boom, it's sorted. Do not use it. It is stupid, but it's kind of funny that it works. So, any questions about bozosort? Yeah, again, do not use it on an exam because, yeah, the other sections have not gone other, like, will not make it to quicksort, will not make it to this, and probably don't want to use this. I mean, if you're brave enough, go for it. Do not hold me responsible if you get a 0. All right, so you have code for it? Yeah.
So for bozosort, we're randomly sorting two elements every time, right?
Yep.
And we only check to see if the final array is in order.
Yep.
So isn't it like technically like a chance where you just keep swapping it?
Yep.
To the point where like you'll never get a sorted array. You just keep swapping it.
Yep. Yeah, so the question is, isn't there a chance where I just keep swapping it and through randomness I just never make it? And the answer is, yep. But due to statistics, right, there's a chance if I give you a coin and I tell you to flip heads, there's a chance you get 1,000 heads in a row. Is it likely that's going to happen? No. So this, I mean, you can calculate the odds to this and see, well, here we can see how many times. Let's see. In count, we can count how many times we actually swap. So plus count. So it turns out computers are pretty fast. We can just see. Let's experiment. So for most things in computers, you can just go ahead. You can experiment yourself. That's what makes software great. You just write more software to check your software. So yeah, that randomly tried like 1,000,000 times. So turns out computers are pretty fast, right? So if you want to see how bad it gets, let's go ahead. If we add a number, let's add another number. I don't know, 50, whatever. So that was what, 1.5 million attempts? So now 2 million still worked, right? Oh, yeah, so rand gives the same thing every time. Let's go ahead and use srand time. Okay, let's get some real randomness or better randomness. Ooh, so that time it was 7 million, 4.3, 5.4. Oh, that was only 500,000, not 5 million. So, but yeah, you can get statistics with this, 2 million, whatever. And I mean, more numbers you add, I mean, eventually your computer's not going to be that fast, right? So let's see what my poor little laptop can do. All right, that's, how many elements is that? That's like what? 10, something like that? Okay, we're probably at the limit of like randomly trying to sort this. All right, my computer's getting hot. Let's see this. There we go. So it is effective up to whatever that is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if you only have to sort 12 numbers, go for it. Kind of breaks down after 12. But, I mean, who am I to tell you what to do? If you go to a job and they tell you to sort something and you use that, you're probably going to get fired. So that's why I have a red text, never use it. All right. Luckily for us, we don't have to write quicksort, so I'll show you how to actually use quicksort. It's actually part of the standard C library. And of course, they had to make it shorter than everything else. Why would they call it quicksort? They called it qsort. Q stands for quick. So it takes a whole bunch of arguments, and it has to do with the limitations of C. But since we know how array works and we did dynamic memory and all that, well, we can kind of realize what all these are. So the first argument is called base. That is just the starting address of the array you would want to sort. Next argument is called n. So it's supposed to be the size of a member or the size of an element, or sorry, the number of members in the array, aka it's supposed to be the length of the array or number of elements. They like using the word member instead of elements, so don't know why. Then third parameter is size, which is the size in bytes of each element. So that's where you can just go ahead and use size of, because you have to tell it exactly how the memory is laid out. And then the third parameter is something really weird. This is not a type we have gone over before. It looks really odd, but that actually just means it wants a function as the last argument. And how this breaks down is it wants a function and then just ignore the name and the star. It means you need to define a function that takes two parameters, and these are their types. So it should take a const void star, aka a pointer, and then another pointer to compare them, and then it should return an int. So how they want the compare function to work is quite similar to string compare. So it should take a pointer to two elements and then return whether or not they are less than or equal to each other. So if the first argument is less than the second, it should return a negative value. If they are equal, then it should return a 0. And if the first element is greater than the second, it should return a positive value. So you can just use -1, 0, and 1 if you want. And that's the same way string compare works, right? If we want to compare if two strings are equal, use strcomp, and then check if the result is 0. So we can actually use qsort to sort our numbers. So here we want to sort this array. So if we want to sort this array, the base is just array because of pointer decay. The number of members is just the length of the array. The size is the size of each element, so it's the size of int. And then we want to write a compare. So compare will take two pointers to elements. So because this is C, we have to tell it what the pointers actually are. In this case, if we are sorting integers, the pointers are pointers to integers. So we can go ahead and just do some typecasting. So we can say that A is actually an int star. And then we can say that B is actually a int star as well. And now these are the proper types. So now we can dereference them and get an int. So if we want to write our function, we could do so we can dereference y or x to get the int value. So if x is less than y, then we know we need to return a negative value. So just to save some space, I will do this and not do a new line. And then I could check if x is greater than, or if x is greater than y, then I return 1. And then otherwise they're equal, so I could just return 0. So that is how you would write a compare function for the quicksort. So now if I run this and use qsort, boom, it's sorted. And now makes it real easy. So if you want additional practice with these, you could write like insertion sort, but instead of going in ascending order, you can go in descending order. And well, that requires, you have to make different comparisons and things like that in the algorithm, kind of a pain. If you want to do that with this compare function, well, if I want to sort it in the other order, I can just flip around the positive and negative values, just like this. And then suddenly, I now get it in the other order because it's using a different comparison function. And you can write this so it can sort whatever you want. You can have it sort structures, sort whatever. You just have to write the comparison function. That's all you have to do. And it will go ahead and then do all that quicksort stuff for you, so you never have to write quicksort again. And luckily, this is as hard as using quicksort gets. So other languages make this a lot easier. C makes it exceedingly hard, but it's not too bad, right? Kind of. All right, any questions about that? Yeah?
Is there a way to pass, like, compare, like, to, you know how in Python you have this lambda, like an anonymous function?
Yeah.
Can you create, is there syntax in C for anonymous functions?
Yeah, so the question is, does C have anonymous functions like Python has lambdas or anything like that? And the answer to that is no. C does not do any of that. So C++ will. But C, the reason why some people like it is, well, the language itself is not that big, it's not that complicated, but it's ugly. It's ugly as hell. Well, it's pretty ugly, and it makes doing some things just like exceedingly hard. So in some languages, you just give it an array and you do like array.sort or something like that, and then boom, you're done. In C, you have to tell it literally everything. You have to tell it details about memory and all that stuff, and it's just a lot of stuff. Yeah?
Are you able to pass functions into other functions?
So the question is, can I pass functions to other functions? And the answer to that is yes. So like here, I passed a function to the quicksort function, right? So yeah.
Even though one
Yep. Yeah, so the syntax is just kind of ugly. So like the type of it is like that weird type, that compare type. That's what the type of a function is. It's ugly. But at the end of the day, in C, it actually just is a pointer. Like functions live somewhere in memory, and it's really just a pointer. But we don't go into that much detail. But once you take the next course in this series and like do assembly that's like closer to the CPU, yeah, functions are, you just need an address for a function. So luckily we do C because, well, if you understand C, then you understand kind of how a computer works. All right, so another example, that quicksort kind of makes it kind of nice. So let's go ahead and solve another problem. Here, I wrote main that takes a bunch of arguments, so I can type in whatever I want. And while using quicksort and I have a string compare, shouldn't take me much code if I want to go ahead and sort all of the arguments. So I can sort them in alphabetical order. So let's see if I run this. Let's say John Elf A Z, I don't know, hello, something like that. So here, remember the first 0th argument is just the name of the program, so I'll ignore it. So if I go ahead and just print them, they'll show up in the order I typed them. And if I want to go ahead and sort them all, well, we could write insertion sort, we could do whatever, but then it's kind of a pain, and then like how to compare strings. Oh, we have string comp, we have to remember how to call it, kind of a pain. So we can try it with quicksort. So we just type qsort, and then we need the starting address of the array. So if I want to ignore the first element, I could do argv +1, right? So I'm just doing pointer arithmetic, skipping the 0th argument. So I want my array to technically start at the 2nd element, right? So want to skip the first one. And then the number of elements, well, that's given by argc. And if I skip the first one, it's -1, right? So if I type in 2, or like if I type in here, I would have, this would be like the first argument, 0th argument, 1, 2, 3, 4, 5. So the size would be 6. So I only really want to sort the 5 I actually typed, so I'll just skip the first one. So I will do -1. And then here it says the size, so it's the size of each element. So the size of each element, well, they are a char star, so it's a pointer to the first character of the string, right? That's null terminated if we remember our strings. And then what's our next argument? So now we need a comparison function, and I just wrote a little stub there. So that would be our quicksort, and now we have to write compare. So you might think that I could just use string compare, right? Do something like that. And that should work, kind of. So you can go ahead and try this. And not sorted, not in the least bit. So why is that? Well, remember that the pointers here, they are pointers to elements. And if our element is a char star, if it's a pointer to an element, it is a pointer to a character, right? So in other words, we would have a char pointer called x, and that's what actually, that's what actually A is. And then B is actually a char pointer to. So to access the pointer of the string, well, I have to dereference that, right? And you can remember dereferencing just kind of takes a star off of the type. So if I dereference x, then I will get a char star back, so pointer to a character, which will point to a null terminated string. So I could do something that looks like this. Oh, not z, y. So now if I run this, boom, it's sorted. Didn't actually have to do that much work, right? It just looks potentially very, very ugly. But if you know C and you know what's going on, it's not too bad, and this is about the hardest thing we will get in this course. Yeah?
So before that, you were just sorting the addresses of the elements, that they were sequential to begin with, so the order wasn't changing.
Yeah, so well, the crux of the question is why, before when I just used string comp, did the order not change? And the answer to that is basically the pointer was pointing to like a bunch of pointers, and all of them kind of started with the same prefix, and then eventually this array, I believe, ends with a null, like a null pointer. So eventually they all had the same prefix and they all ended with a 0. So the pointers just kind of grew. So it would essentially just be the same order that I defined the pointers in, just by chance, essentially. So the only reason why I got the same order is essentially more or less by luck, because my computer laid out memory in that exact way, and I interpreted the addresses wrong because they were actually pointers to pointers, but I interpreted them as strings. So potentially anything could have happened, including it could have crashed, but it just turned out that didn't do anything. So yeah, debugging that would have been very, very difficult if it like kind of works sometimes. But yeah, any questions about that? Because that's about the hardest thing we will ever see in this course. And like I said, this is completely extra. So if you need to write a program, I would suggest not writing your own sorting algorithm and using qsort, even though it's a kind of a pain in the butt to use. Just remember the rules where this compare function, they are pointers to elements. So if you want to access an element, you have to dereference it. So that's the only thing you really have to remember. All right, so here's the code so you have it in slides. And then, yeah, typically from here on out, like it's good to like practice writing sorting algorithms. It's really good practice in C, especially since small errors will just produce the wrong result, or you'll have memory errors and it'll crash. But likely in any real program, you'll probably want to reach for something like quicksort, and it's a fairly difficult function to use, but it's still better than writing quicksort by hand. You kind of really have to understand memory, the limitations of C, because C has to use like a void star to be general, which aka just means it's a pointer to something. C doesn't know what it is, and you kind of have to tell C what it is and cast it, and that's really error prone. So the primary design for a language like C++ that you will use later, and pretty much any other language that's not C, is to make things like sorting really much easier to do and also much more efficient. So you don't have to do all that weird stuff we had to do before. Usually, like I said before, you can just like take an array and then do array.sort, and then boom, it works. But this is how computers actually work. At some point during that, a quicksort is going to happen. So with that, I will stick around if you have any other questions, but just remember, pulling for you, we're on this together.